Hello, everyone. My name is Yurganov. I was born in Russia and lived there until 1995. Since 2006, I was affiliated with the University of Maryland, Baltimore County. I'm retired now and live in Columbia, South Carolina. I am a spectroscopist by training. In Russia, I used ground spectroscopy to measure the total column abundance of carbon monoxide in the atmosphere. The main content of my report is related to the possibility of measuring carbon monoxide in the lower and middle layers of the atmosphere separately. This looks possible due to the fact that the existing satellite instruments have different sensitivity dependencies on height, especially and significantly different. This approach will be applied to study wildfires in various locations around the world. The focus will be on eastern Siberia. In addition, carbon monoxide from tropical fires and forest fires in Canada, in Australia, will be analyzed. The issue of the relationship between above ground and underground coal fires will also be considered. However, first, let me take a short excursion into the history of the issue. A brief overview of our spectroscopic measurements of CO in the 70s and 80s of the last century will be given. Carbon monoxide lines in the solar spectrum near 4.7 microns were identified first in Columbus, Ohio, by a Belgian astronomer, Marcel Bijot. John Shaw measured carbon monoxide total column density also in Columbus in 1952-53. Our continuous CO total column measurements near Moscow using a similar spectroscopic approach started in 1970. Here you see a coelostat on the roof of our Zvenigorod laboratory. Solar beam is directed by a system of mirrors downward to the spectrometer. And examples of spectra obtained by John Shaw in 1951 or 52, and our spectrum we recorded in 1971 are given. And also you can have an idea what kind of personal computers were used by us. Over the next 15 years, these observations were extended to several regions of the Soviet Union using a trailer sea cruises Even Antarctica, on the Antarctica station Молодежная in 1977, and once again in a couple of years later. Also in the Arctic. All these measurements were made using a homemade spectrometer nicknamed sarcophagus, with automated sun tracking system, also homemade. Our boss, Vladimir Ivanovich Dianov-Klokov, designed this instrument, and in the machine building workshop of our institute, the spectrometer was cloned in many copies. The results of first 7-8 years were summarized in a doctoral dissertation in 1979 and in the article in TIR journal in 1981. Participants of our team. Evgeny Grechko participated in field work and directs the activity, scientific activity at the Zvenigorod station. Anatoly Zola also participated in many field campaigns and is responsible for maintenance of regular measurements in Zvenigorod now. An important part of this work was improvement of the retrieval procedures. Viktor Tarabukhin, this youngster, and this gentleman, and Nikita Pugachev developed a forward model for absorption of solar light in the atmosphere. This model was based on the atmospheric line parameters compilation by McClatchy, published in 1973. Now, this compilation is known as ITRAN. In 1980, the Moscow part of our lab hosted a colleague from Germany, Wolfgang Zeiler, the Max Planck Institute for Chemistry in Mainz. He was a pioneer of CO and methane studies. What did we learn about the cycle of carbon monoxide? This is latitudinal dependence measured during sea cruises. Significantly higher CO content in the northern hemisphere compared to the southern hemisphere indicates the significant role of anthropogenic production for its cycle. A hump over tropics was related to wildfires, and these wildfires further were investigated specially. The seasonal cycle of CO has a maximum in March and minimum in late summer, in August. The seasonal drop of CO from winter to summer is explained by intensification of photochemical sink in summer time. The empirical two-dimensional model of latitude time distribution of CO was proposed by us in the same. The main idea of these two articles was to determine the influence of the Siberian fires in 1998 2002 and 2003 on the carbon content outside the fire zone. Each point is monthly anomaly of total CO column, these two panels, and surface concentration, these two panels. The measurement sites were scattered over the northern hemisphere. It was found that CO anomaly does not depend on the geographical location of the site. The differences between anomalies in the surface layer in the total column also were insignificant. In our current report, a similar investigation is carried out, but now for the fire zone itself and based on satellite data. Why is the case of Siberian fires so important? First, you need to keep in mind that the nature of Siberia is diverse. Western Siberia is an area of swamps. Southern Siberia is occupied by boreal forests, Russian word taiga. The blue line is southern edge of the permafrost. Also shown are areas of the Tunguska and Lena coal basins. They are largest in the world. The figure shows the annual CO wildfire emissions calculated in GFED4 database. Red line is total Russia. Black line is for central Siberia, permafrost and coal area. During the beginning of this period, emissions were very low. That shows that practically no large fires happened during this 10-15 years. But after that, emission grew and reached 90% of total Russian wildfire emission. At present, there is no comprehensive explanation for this picture. Why is the emission of gases from areas covered by permafrost growing? It's enough fuel for combustion in the boreal forest, but what is burning in permafrost area? I hope that the satellite measurements presented in this report will help to resolve this question. Our report is based on measurements of the total CO amount in the atmosphere above various types of wildfires using two different instruments, ERS and TRAPON. The main difference between them is different sensitivity to the atmospheric boundary layer, the thickness of which is known to be 1.5 kilometers. Everson kernel characterize the dependence of the sensitivity of the instrument on height. The left graph shows the kernels for airs and similar instruments. The right graph is for tropomic, for different cloudiness from 0 to 0.2. The left graph shows that for the boundary layer, sensitivity of tropomy is 2 to 3 times higher than that for airs. In what follows, you will see how this difference affects the measurement of these two instruments. The next will be a set of daily XCO maps of Siberia in 2021, smoothed by 5 days running average, shown date plus minus 2 days. XCO are reproduced in the same units for both instruments from 50 to 350 ppb. The third graph will be just a differential between these two maps, tropomy minus airs. Black contour maps are for 110 ppb. And for delta XCO, these lines are correspond to 20 ppb. This example is for maximum burning in August. This burning, and this is this, and no, here is anthropogenic pollution in China. Tropomy can see this high CO in China, and airs doesn't. The meaning of this XCO for tropomy is total column. Average mixing ratio for airs is mid-troposphere average because of special averaging kernel. You could see it. Delta XCO is just a difference between these two values. Beginning of this set is in June 2021, and in June there were no fires, but you can see clearly the background XCO for both devices, and both devices have the same background between 80 and 90 ppb. And background for delta XCO is 0. Now it's the 2nd of June, nothing happened. 3rd of June, 4th of June, anthropogenic urban pollution in the same place. For all the days changes day to day a little bit. And only on 17th of June, a small spot appeared of emitted CO from fires. That's the beginning. And nothing is on the AS map. Still nothing else and small. And now some first signs of high CO appeared at the AS map. Growing. And you see that the boundary layer CO, low tropospheric CO, going to the upper troposphere and mid troposphere, and now it can be seen by AS2. Going further. Now we see that mean tropospheric CO measured by tropomi and mean mid tropospheric CO are practically very similar. With, so that means that convection due to high temperature on the in the boundary layer in conditions of strong fire lifts to the higher altitudes. So this fire is most clearly most possible is forest fire. And on 13th of July, a new pattern appeared. Step back and then on. And this is a matter of low tropospheric CO case. Especially here, you see that low tropospheric CO prevails over mid-tropospheric CO. The troponin can see the low tropospheric and AS can. At the end of July, the fire is growing in the central part of Siberia, in the area with permafrost and the coal basins. Later, I will speak about that more. Very strong fires in this area. And also polluted mid-troposphere too, but not so strong as in the boundary layer. This is close to maximum of this fire. And transport to Arctic is going on. To the Arctic and to the east. But now the fire is diminishing and the wall is dispersed over entire high northern hemisphere. As a result. These maps of August monthly mean XCO according to Tropomi and Earth measurements. The bottom map indicates locations of two cold basins. These locations were repeated by a shaded area at both these maps. Increased CO content in the entire atmosphere was observed within the boundaries of these basins. A similar but less contrast picture was observed in free troposphere by Earth. Australia fires. These fires occurred in Australia since November 2019, and it was in the southeastern part of Australia. In November, early December, only Tropomi could see this CO from this fire. And S was just a little bit sensitivity to this fire. So everything can be seen only in Tropomi. But next fire was a little bit different from the first one, and at some moment, CO appeared in the free troposphere and was growing and transported westward, both in the boundary layer detected by Tropomi and in free troposphere detected by AS. Westward. And a new fire at the end of December started, and this fire was low temperature, probably fire, and the flux was from from the main from the eastern shore of Australia to the east. And interesting that Earth was absolutely blind to this CO concentrated in the lower troposphere. absolutely blind. Only this parts, only during these days, some intrusions of polluted air into the troposphere were detected by Earth, but mostly nothing. Coal is an important energy resource of Australia, and in summer of 2019-2020, wildfires occurred in the eastern shore of Australia and southeastern, and the plot on the right shows the daily mean CO, XCO registered by troponin, and you see very good coincidence between the contour of Sydney coal basin and high values of CO. Record fires burned in Canada in summer of last year. In June and early July, this fire burned in Quebec. And you see that troponin clearly see the high CO and Earth does not see much CO there. And of June, high CO detected by troponin and not high CO, not so high CO detected by Earth. And this CO in the boundary layer is transported to the south and caused pollution, high pollution in Boston and New York City. Later, in middle of July, started fire in western provinces of Canada. And the fire was seen both by troponin and by Earth. That means that this fire are probable are forest fire in boreal forest of Canada. All the troposphere was polluted in boundary layer and free troposphere. July. Now the burning area of Canada, to be more specific, the CO, high CO in Canada covers practically 100% of Canadian territory. And now it is going both to south and to the Arctic. Very different picture comparing with Australia. And final case is CO from tropical fires. We start with early June 2021 and going on Trapomi see the fire in tropical Africa, but do not see any fires in South America. Yes, I can see nothing practically. Going on, going on, going on. And middle June, it appears free tropospheric CO in late June, but not much. Ultrapospheric mean CO is growing in Africa, and still nothing in America. The picture is very quiet, quite different from mid latitudes. Very high CO in August in Africa and starting fires in South America. Earth can see significant values of CO at CO in mid-troposphere. Growing in both continents, but still mid-tropospheric CO in South America are not so high. Starting transport southeastern direction, southeast. September, and now there is a tendency to unite between these two fires, and they joined only in the boundary layer. The troposphere, different picture. Again, joint in boundary layer, according to Traponi. Very nice picture, right? Oh, let's look at 3 examples. Measuring carbon monoxide with these 2 instruments during megafires revealed a wide range of different pollution events in the lower and middle layers of the atmosphere. Australian fires polluted only the boundary layer. During tropical fires in South America and Africa, the patterns of air pollution on the same day were the opposite. Forest fires in Canada have polluted the entire troposphere. This data will help to reveal the nature of combustion processes during megafires. Now, preliminary discussion. The pre-tropospheric and boundary layer pollution in fires can be easily recognized by comparing tropomi and air data. Vertical air mixing during fires depends on the combustion temperature. Smoldering fires, peat, coal, and to some extent brush fires, usually lead to boundary layer contamination, but not for free troposphere. During boreal forest fire, especially crown fires, high temperature combustion predominates, pyroconvection develops, combustion products enter the free troposphere and can be recorded by airs. It is possible to formulate some preliminary conclusions about the nature of the considered wildfire. For example, fires in Canada, western provinces in July-August 2023 were predominantly forest fires. The Australian fire was characterized by contaminated boundary layer and relatively clean pre-troposphere. The role of fuel in these fires could be played by coal, peat, and/or shrubs. The 2021 Siberian fire was more complex in nature. The 2021 and 2023 Siberian and Canadian events took place at unusually high latitudes. It's not enough to simply attribute this effect to climate change. There must be special mechanisms that for this shift to the north. Siberian and Australian fires coincided geographically with coal deposits. Is this a fortunate coincidence, or are coal fires really growing along with climate change? There is no answer yet. Further development of this approach requires a more detailed inclusion of a priori CO profiles and averaging kernel in the analysis, preferably at the pixel level. Thank you for your attention.